You're listening to Gradient Dissent, a show about making machine learning work in the real world, and I'm your host, Lukas Biewald. So I'm out of my garage and in our beautiful office in the Mission, and today I'm talking to Sergiy Nesterenko, who is the CEO and founder of Quilter AI. And Quilter is a super cool company because it automates PCB design, and PCBs are in pretty much every piece of electronics that you might use. And it's an amazing example of a company that's actually using reinforcement learning for real-world applications. I remember Andrew Ng in his course years ago telling me that there really were no reinforcement learning applications working in the real world. And well, here's one that's actually working. And Sergiy talks about not only his company, but how he got into the field of machine learning and became an expert in reinforcement learning. And some of that dates back to Andrew Ng's class, which I took as well. I hope you enjoy this interview. All right, so Sergiy, you work on AI applied to PCBs. And so when I was first researching you, I was kind of realizing I have this vague sense that PCBs are those green things inside computers and other electronics, but kind of realized I don't really exactly know what a PCB is and why they're important. So maybe you could start by talking about that.
Yeah, gladly. So I brought props. They don't have to be green. They can be any other color, but this is what we're talking about, right? So this actually is just a computer motherboard. And what it really is it's basically fiberglass on the inside, and then a bunch of different layers of copper and insulating materials. And the job of the PCB is to basically connect a bunch of the components. So if you look closely at the PCB, there's all these capacitors, power components, there's a CPU here, a GPU plugs in, all of that good stuff. And you can really imagine that a PCB is just like a bunch of wires, right?
Mm-hmm.
You're connecting those components together. But of course, it's not quite that easy.
And why is it not quite that easy? I actually just imagine it as essentially a bunch of wires and places to solder things into or push chips into. What makes it more complicated?
Yeah, so basically physics, right? So all of the communication that's happening between those chips, you cannot assume that the connections the PCB is making are ideal, right? They have some resistance, they have some inductance, and so you have potential signal degradation over those signals. The board can potentially heat up. And in general, especially once you get into multiple gigahertz, 2, 4, 5 gigahertz, your wavelength of the communication is about on the order of the size of the PCB, which means that all of the wave dynamics that happens in electromagnetics is now occurring on your PCB. And so you kind of have to account for all of the imperfections that are going to happen as a result of you having a physical object and account for them in the design.
Interesting. So what's an example of some way you might modify the design to make the board work better?
Yeah, so in general, the big issue with designing the PCB is just are you confident it's going to work at all, right? So this kind of board that I'm talking about, right? So, this is, I haven't counted, but probably hundreds of components and thousands of connections. And you're talking about drawing all of these little wires on the back. And then there's probably another 10 or 16 layers inside of there that are vertically kind of looking similar to that. So it's very time consuming. This is done manually today in almost all cases. And so somebody's sitting at something that looks like Photoshop or Paint, but more specific for PCB design, of course, and is drawing all of these connections. And that could take, for a board like that could take months. So what you really want to do is you want to make sure that when you're finished, the board actually works, right? And this is quite common that you fire up the board for the first time and not everything works on it, right? And so you're trying to figure out why, trying to debug it. And then eventually you'll have to do things like pass FCC testing to make sure that the board is not kind of creating too much interference with everything else. So an example of something that might go wrong that isn't obvious. Imagine you have two of these wires running next to each other, and they have some sort of high-speed communication going along them. Maybe it's like a DDR connection to a memory or something like that. You'd think that, wire goes from A to B, different wire goes from C to D, and that's it, and they stay isolated. In fact, that's actually not the case, right? The wire is basically an antenna. It creates electromagnetic energy. That electromagnetic energy couples into the other wire. All of a sudden, you've got noise on that wire. And so that could then ruin some sensitive signal or ruin that communication or whatever else. So this is called crosstalk. So figuring out how to make that not happen is one of the things that you might be thinking about as you're designing a PCB. And this way, many different ways that it could kind of happen, many ways that the geometry that you set up kind of leads to it. But in general, like, keeping them far apart is a good start.
And really the only way to test it is by manufacturing it and trying it. I mean, we've talked to a lot of different roboticists on this show and talked a lot about, kind of simulating mechanics in the real world. Why is it so hard to simulate, I guess, the electromagnetic interactions here?
Yeah, so it's practically difficult, not theoretically difficult. So like all of the physics is known, right? It's just electromagnetics, it's just Maxwell equations, there's a million different solvers for them, you can set them all up and that kind of stuff. That's fine. But practically speaking, like, there isn't just a tool where you like submit your design, click go, and like CI/CD runs and checks all of the different things that could go wrong, and you get a thumbs up or a thumbs down. Instead, like today, as a designer, you have to know what question to ask. You have to say, oh, I'm worried about crosstalk specifically from this trace to this trace. Let me then go into a simulation tool and model it out and run the simulation and so on and so forth. And practically speaking, like most folks that are designing boards, have limited or no experience actually doing the simulations. So a lot of times people just say, well, I followed the rules I typically follow. It's probably going to be fine. Let's just order it. It'll be on my desk in a few days and we'll find out. So it's definitely possible, but just the tooling isn't so good that you can actually click a button and go through all of it that easily.
But isn't it pretty bad if they fail? Like, doesn't your whole device then not work?
Definitely. Yeah, absolutely. So, I mean, this is where the iteration begins, basically, right? So if you typically don't go and straight like order 1 million units for your device and go into production. Instead, you would, do a prototype run where you do a few boards, you validate that everything works. Anything that didn't, you debug, figure out why, make changes, go through a few revisions. And then when you're kind of really confident that your design is good, you go and ramp up to production, for sure.
Okay, and so where do you come in? Like, how are you improving this process?
Yeah, so what we're trying to do is to automate the layout process. So to elaborate, designing a board is roughly 3 major steps, right? The first is creating what's called a circuit schematic. So you can picture a circuit schematic kind of like a block diagram or a flow chart where you basically have like, these are the chips I'm going to use, here's how they're connected, and so on and so forth. So by analogy to software, I think of that kind of like writing code, right? That's where you're specifying like what is the inputs and the outputs of your board. You can think of the chips as kind of like libraries that you're using with some off-the-shelf functionality and so on and so forth. The second step is called layout. So that's where you take that schematic and actually convert it into a blueprint for, actual fiberglass and copper that implements that schematic. So I think of that as kind of compiling your code, right? The job of the circuit board is just to make the schematic real. And then once you have those blueprints, you can send it to a manufacturer. A manufacturer can put it together. You get it back on your desk and, you find if there's issues and you repeat. So what we're trying to do is we're trying to take layout, which is today completely manual and time consuming, and we're trying to automate it completely.
And how are you doing that?
So the approach that we take overall is by using reinforcement learning. So the way that we see this problem is that you can kind of think of PCB design as a game, right? Like at a simple level, you've got, big box and you're putting little boxes in that big box and then you're connecting them, right? And so the way that we are setting this up is that we've got, this kind of simulation or engine that's running this ability to place components, to route components, so on and so forth. And then eventually, once the board design is completed, it gets passed to a bunch of physics tests. So that's us building out the kind of like CI/CD of enumerating every single concern and making sure that they all actually work. And then you can feed that signal back as a reward and then train an agent to get better and better at this game. That's roughly how we're approaching this.
So is the physics simulation also done using machine learning, or is that like a set of tests based on laws of physics, I guess?
Yeah, so this is something where we're evolving over time. So the first thing we actually did when we started this, we used a full wave like Maxwell equation solver, just classic off-the-shelf open source implementation that's used by a lot of researchers and well validated. But we found that it's just too slow. right? So we have this issue that like running even a single simulation, despite it being GPU accelerated, can take 20 or 30 minutes, something like that. And you would have many of those to do throughout the board because you have many, many different questions. And of course, in a reinforcement learning context, that's quite painful and slow. So what we're doing now is we're going back and seeing whether we can use either heuristics or much simpler simulations along the way as those reward signals. So, you can encode conservatively some of the concerns as just raw geometry, or by doing analytical approximations to the Maxwell equations, or by doing approximations like quasi-static, things of that nature. And like that's a part of the research that we're in right now, is figuring out what that's all going to look like exactly.
Interesting. And so what's the end result of this? The more reliable PCB?
Yeah, so I think that there's roughly two pieces of value that we'll focus on overall. The first one, and the one that we can actually kind of deliver on today, is time, right? So the most important thing, in my opinion, right now is that, even a simple board could take a week to design by hand. And that's a week that you're not testing it, that you're not building the firmware for it, that, you're waiting to ship your product, basically. And so we can compress that from, a week or 2 weeks or whatever it is down to an hour or two, and release that bottleneck. That's probably the first thing. The second benefit of that, of course, is now you have an engineer who has time to go focus on something else, right? They can be focusing on, validating their parts list, or on initial bring up, or on writing the firmware, or on their next schematic design, or whatever else. So time is really the first major benefit that we're focused on. I think eventually, like not today, but eventually, I do think that we'll be able to design better boards than people. And the reason for this is that when you design a board and it's going to take a long time, you stack a lot of margin, right? Like you make the board a bit bigger than it has to be because you're worried about running out of space. The things like crosstalk and whatnot, you assume some conservative rules to make sure it's not going to bite you. And because of that, I think that, there's probably 10% or more margin in basically every single board out there. And so eventually, when we can do this job better than humans can, there's potential to design better boards than humans can.
It's funny, I would think it would be easy to design better boards than humans can, right? If humans are just sort of laying things out by hand, this doesn't seem like a task that humans are designed to do very well. Is it really so hard to get superhuman performance?
It is. So this problem, it's very interesting. I mean, this has been researched for 60 years now, right? So the first papers on automating board design are from like 1961, 62, 63. They were doing things like graph embeddings and planes to try to model this problem. And like practically speaking, those tools just still don't work, right? Like nobody does their layout with an automated tool. Auto routers are notoriously hated in this industry. So it's, making a machine that can actually do this has proven difficult just historically. The basic intuition for why it's hard, like it's funny because we as humans are actually really good at spatial reasoning. And so to us, this problem seems pretty easy and it would seem like a computer would be good at doing it, but it's definitely tricky. So I'll give you one piece of intuition for how. Let's forget about all the physics. Let's forget about, imperfections in manufacturing and all that stuff. Let's just focus on placing components and routing them, right? Like connecting the dots. If you've placed your components, routing your first trace is really easy, right? You've got a start point, you've got an end point, you've got some obstacles. That's a maze solver, right? CS1A kind of problem. The difficulty comes up in that when you've solved that problem, that solution is now an obstacle to your next puzzle, to your next maze. And so the real challenge is, how do you make sure that your 10,000th trace still has enough space to be completed, right? If you just kind of greedily connect the dots, you'll surely block yourself off and not be able to complete. And if you don't complete, the board definitely doesn't work. Mm-hmm. And so that's a deceptively challenging problem to solve that humans are actually pretty good at.
That's really amazing that computers can beat the best Go player, but they can't lay out a bunch of wires better than a human. It's kind of blowing my mind. Is part of it the sort of like fuzzy constraints of like you might move, something on the board or something like that?
I mean, I don't think that there's any kind of like fundamental reason for this, right? Like I'm sure if DeepMind had chosen to tackle PCB layout rather than Go, they probably would have done a good job. And also you don't necessarily even need a superhuman ability in order to make a useful product, right? Like even if you have the ability to do, the easier half of all the board designs out there, that's already very useful. So I think that, it's definitely a problem worth solving and can be solved. I think that the difficulty is, there's a few pieces of difficulty here, right? So one is just the raw combinatorics, right? Like you have, tens of thousands of traces to eventually do. Some of the bigger boards, like, these server cards for mini GPUs could have hundreds of thousands of traces. And for every single one of those traces, there's a lot of different ways that it could go. And just exploring all of them is not possible, right? So you have to have some level of intelligence, some level of pruning to figure out which strategies are going to work. Of course, just connecting the dots isn't sufficient. You have to account for the physics, and that's kind of the second big difficulty, is even if you've connected the dots, that's still not good enough, right? You still have to go check those constraints. I think that's kind of what it is. Just huge combinatorial space and a lot of important manufacturing and physics-led constraints.
And now you've started to build a company around this and really take on real-world challenges. What's happened in that process? Like, you've laid out a very clear, well-defined, reinforcement learning problem that I think, every grad student would be jealous of. But I'm quite sure that as you've built a company around this, you've come across surprises. Like, what have been some of the surprises and learnings along the way?
Oh, lots. There's no part of starting a company that isn't full of lessons and surprises. I think probably the most interesting thing for us to balance and try to figure out is like, how do you simultaneously invest in, basically research of like solving this very difficult problem, but also make progress on finding applications early, delivering something that customers can actually start to use. And that's definitely tricky. That's something that we spend a lot of time focusing on. So we've released our tool in an open beta that people can just kind of upload boards and try it out. And we're encouraging people to build these things so we can see what happens and learn from it. I see a lot of people submitting designs. That's super exciting. A lot of the designs are things I didn't think people would be doing. People are learning to use this in interesting ways. So, like, I'll give you an example. We saw a person submit basically the same board 10 different times. And we were wondering, like, what are they doing? Why are they doing this? Because, you typically think, like, I have one code base, I click compile, it comes out, and there's my board. Like, I'm done. And what this person was telling us is that they were trying to figure out how small they can make the board. So what they ended up doing is just giving it like 10 different constraints in terms of sizes and just say, route all of them. Let's see which one works. And they were saying that like it's changing how they're thinking because now the layout is kind of free. Whereas before they had to like pay someone and ask someone to go and do this. And so they would never like explore a bunch of board sizes if they had to kind of pay for it and wait and all that stuff. I think that is showing that like when a compiler starts to exist for electronics, like the way that we design electronics is going to change pretty drastically. And I think that is the most exciting thing to me. And that's where I'm, most looking forward to all the lessons.
Well, why do you say when a compiler exists? It sounds like you've made a compiler and released it. Are there things that hold it back from, from everyone using it?
Absolutely. So we do not claim that we've solved the whole problem. We're far from it, frankly, to get to the point where we can solve any kind of board out there, right? So there's two axes of complexity that we're measuring yourselves against, roughly speaking. One is just the raw combinatorics. So, how many components can you fit on the board? How densely? How many pins are there to route, right? That's kind of one set of problems. And then the other is the physics, right? So what kinds of physics concerns can you take care of? So, on the combinatoric side, we are currently solving boards that are about, 1,000 to 2,000 pins at the maximum, which is like, okay, for simpler boards, that's certainly fine. For some test boards, it's certainly fine. But like, that's not nearly enough for like a motherboard, right? Your CPU alone has like 1,400 pins, never mind all the other components. So we have to improve by an order of magnitude to get to the point where we're doing like a computer motherboard, even combinatorially.
Wait, can I interrupt? So,
of course.
Yeah, I've like put together, I don't know. I've looked at a motherboard. The CPU is like 128 pins or something, isn't it? Why does it have so many pins?
If I'm not mistaken, I'm thinking about the LGA 1147 socket. And I think that's the one that has that many pins. It's pretty extraordinary. I'll have to double check the exact number at the end, but it's
like thousands.
I don't think it's multiple thousands, but it's over 1,000 for sure.
Just to connect the CPU in. Wow. Okay.
Yeah, exactly.
And then I guess there's tons of other things that it connects to, which makes for more pins.
Exactly. Exactly. So, your CPU is connecting to your memory, to your audio system, to your HDMI, video, all of that kind of stuff eventually ends up going through the CPU. And so you're doing all of that in parallel through all of these pins. And then, of course, each of those components has their own, breakouts, their own complexity, so on and so forth. So it's quite easy to get into the tens of thousands of pins on a complicated board.
And the wires, can they cross? They can't cross, right? Like, what do? They go underneath each other or above each other or something like that?
Yeah, you can imagine it kind of like, what's a good analogy? Like a building or a parking lot or something like that. So you have these layers, and the layers are just planes of copper, and they're isolated by insulating materials. And so you can take arbitrary shapes in 2 dimensions on any given layer, and then you basically drill a hole in the PCB and install kind of like a rivet. And so that's a via, and that's what allows you to jump between layers. And so the puzzle is to basically arrange all these wires across all of these layers such that they obviously don't intersect when they're not allowed to, but of course connect all of the start points to all of the end points.
And can you always add layers? Like, I guess I'd imagine if you could always add layers, you could eventually do it, right?
Yeah, certainly. If you just added as many layers as you had nets on the board, then this is a trivial problem, because you still have to find a place for the vias to jump down to those layers. But layers they increase your manufacturing cost and complexity, right? So a very simple board will have just 2 layers, right? And if you're trying to make a really, really cheap board, that's what it'll be. So like if you've ever seen a Arduino Uno, right? That one will be a 2-layer, well, the old one, the R3 was a 2-layer board. And that just makes for cheap, fast manufacturing. 4 layers, more expensive, 6 layers, more expensive. And practically speaking, like probably the biggest stack-ups that are around today are in the 50, 60, 70 layers kind of thing. That's usually where you top out. At that point, it just becomes hard to manufacture.
I'm picturing an Arduino Uno. I think I had one of those back in the day. Maybe not Uno, but I think so. I mean, Arduino has quite a lot of pins, doesn't it?
So
how does that work? Like, I would think with 2 layers, it would be impossible to connect all the pins to the Arduino, what do you even call it? Microcontroller, the chip?
Yeah.
Well, wouldn't they have to cross somewhere with 2 layers? I mean, how does that work?
No, definitely possible. I mean, a lot of boards are 2 layers, and even relatively complicated boards. Like I've definitely seen boards that have thousands of pins that are 2 layers. Even more fun challenge is when you make a board at home. So like you can actually do the process of etching a board yourself pretty easily at home. And the easiest way to do it is a 1-layer board. And so at that point, then that becomes really, really challenging how to not intersect. At some point, you can only handle very low complexity with that. But roughly speaking, these wires, right, they're relatively thin. And so you have a lot of space to kind of put them side by side with each other. And then where you have to have a crossing, one of the wires takes a via, jumps under, goes on the 2nd layer, and comes back up. And so that's roughly how you de-intersect them, is where you were going to have a collision, jump one down to a different layer, cross over, and then jump back up.
Oh, I see. And it can do that at any time.
Yes, exactly.
Because I'm pretty sure with the 1-layer board, I'm digging deep into my math undergraduate, but I'm pretty sure there's some proofs that you can't do arbitrary graphs on a 2D plane, right?
100%. Yeah, there's a theorem called the Kuratowski theorem, which states the kinds of graphs that you cannot embed in planes. I think it's actually an if and only if kind of statement where you basically show that like a fully connected 5 graph and some types of 3 graphs, if you have those, it's impossible to embed. And so, at that point, it's definitely impossible.
But I guess with 2 layers, everything is possible. It's more like physics that gets in your way. Is that right?
Yeah, physics plus manufacturing tolerances.
So
all of these, these wires are real. They have to be manufactured with real dimensions. And so, for example, like a typical manufacturer can make a wire or a trace that's, say 5 mils wide or 5/1000ths of an inch. They also have to respect some separation because if you get too close, the etching process might not etch them apart correctly, and you could have a short where wires are connecting when they shouldn't have been connecting. That might also be 5/1000ths of an inch. And so at some point, if you have a lot of density, these wires end up stacking with each other end to end to end to end, and at some point you just run out of space.
Okay, so I took you down a long digression. I apologize, but it sounds like you could do boards up to a few thousand connections, which sounds like that would be like a lot of the boards out there. But I mean, what else is kind of keeping you from making this in production everywhere?
Yeah, the physics is definitely the second biggest part. So at this point, we are basically one consideration at a time, adding the different constraints that we can handle on these boards. So for example, if you go to Quilter today, you'll see that it has consideration for power, right? So you can do like a 2 amp or 4 amp kind of power supply, which is nothing crazy, right? Like you're not going to run an electric car with that kind of current, but for like a stepper motor or something like that, that's kind of plenty. And so that's something that you'll see, and Quilter will intake, it'll check that it does it correctly, and then when it gives you the result, if we weren't able to guarantee that trace isn't going to basically burn in your hands, then we'll tell you that we failed to generate the design.
Okay, wait, I'm thinking, sorry, I mean, this is like a basic primer on PCB, I guess. But when I think about power lines, it's the high voltage lines that need like special treatment and bigger things. Why did you say it's the amps that constrain you on a PCB?
Yeah, so it's both. So the issue with high voltage is that above a certain level, like above 50 volts, you have to start considering dielectric breakdown and arcing, right? So if you have two, 100 volt pieces of copper next to really, really close to each other, they will break down and ionize air and it'll spark. And that's obviously not good. And so that's not something we currently support, actually. And so, please don't upload a 100 volt board to Quilter and hope that it works, because it probably won't. The second is the current, because the current is what drives the heating. So your wire is basically a resistor, right? It has some amount of resistance, and so as the current is kind of going through it, it's going to heat up. And so typically PCB designers will do a little bit of math to figure out, hey, I want to make sure that this copper doesn't rise more than 10 degrees Celsius above ambient, and then you have to figure out how wide to make that wire, basically, to then drop the resistance to a level where it doesn't overheat.
I see. So the thicker wires are for more current.
Yes, exactly.
Got it. Well, that seems like something you could handle. That's just another implementation detail?
Yeah, exactly. So that one's pretty easy, pretty straightforward. What we're focusing on now is going to get us into higher speed boards. So there's this type of signaling that happens on high speed boards called differential pair. So where you're sending a positive signal on one wire and a negative signal on the other wire. And then at the destination, one of them gets inverted, you add them together, it cancels out the noise, and you can communicate faster, basically. And so there's some kind of special geometry to how thick to make those traces, such that basically the speed of light in them is matched to the starting and end points. How far away they are from each other to control what's called the differential impedance between them. And then you have to run them really, really close together, because if they do come apart, then they'll capture a magnetic field going between them, and that'll introduce opposite noise on the two different wires. And then when you invert them, that noise will amplify and do bad things. And so that's something we'll ship here in a few weeks that'll allow us to do much faster designs, which will be fun. But after that, there's a lot more things we'll have to add.
And now what about just making your models work? Because I think that's an interest of a lot of people that listen to this podcast. Like when you're trying to adapt your models and kind of make them ready for prime time, if you had to kind of change the way you build them, test them, deploy them, all that?
I think probably one of the benefits of reinforcement learning is that you can give your models as much or as little control as you like, right? So for us, the agent playing the game doesn't look like, what a human's doing. It doesn't look like it's like taking a trace and, moving it 1 pixel right, 1 pixel up, 1 pixel right, 1 pixel up, that kind of thing. We take a lot of that complexity and just actually move it into classic code. And really what the models are doing is kind of higher level planning, right? So instead of saying 1 pixel right, 1 pixel up, it's go from here to here, go roughly this way. And then a classic set of code actually fills in the details of how to get that done. So we handle a lot of kind of constraints, not by hoping that the model gets it right, but by just like enforcing it as a constraint in the game, where it's just like an action that the model can't take if it's going to be wrong. Now, testing is definitely a problem. We whenever we make changes, whether it's to models or to actual code, we have to run a lot of regression testing. And that's challenging because we have, we want to run at least, 20, 30, 40, 50 boards through this kind of regression testing and more over time. And each of those takes substantial amounts of time, right? So for even 6 months ago, a lot of those were taking 10 hours a piece on a cluster with a whole bunch of compute resources. And so that makes for a not very fun development experience to sit around and wait for, a day and then see that like one board dropped by 1% completion, and like that's a regression and you have to figure out why. And that's not easy either. So yeah, we invest a lot in trying to make those regression tests much faster, but also getting a lot more information out of them so that when they fail, we have a lot more information about why rather than guess and checking why.
Well, how do you make these regression tests faster? Because you actually have to run this reinforcement learning algorithm, which famously takes a long time.
Yeah, I mean, the biggest lever that we've pulled over the last 6 months is taking a lot of our the research grade Python implementations of these not the models, but the environments that we're running for the RL, and switching them to C++ and paying a lot more attention to speed. And so that's been a huge set of speed ups, primarily on the kind of routing side. Our placer was already pretty fast because it was already written in like CUDA kernels pretty much directly. So the nice thing about that is, if you make your environment faster, it's much easier to train. Your cycle times get a lot lower. You can run faster in production. You can explore more candidates. And we've taken a lot of boards that were taking us like tens of hours before to now, a few minutes with these changes. So that's probably the biggest way. Is just invest in making the environment as fast as possible.
Is there anything else that you've added to your stack as you've tried to get that last level of reliability so you could deploy it to customers?
I think it's in terms of the reliability to customers, we're going to be adding stuff all the time. Like, I think the biggest thing that we are currently not doing well enough is making it very clear to users like what kinds of considerations we can handle and what kinds we can't, right? So a lot of people will come to Quilter and upload a board, and they'll just assume that it's like magic and that it can like read and understand all the schematics and that like it'll figure out all the high speed stuff and all the high current stuff and everything. And then like they see the result and they're like, that's clearly wrong. It didn't do any of that. And I think that's our fault for not basically saying like, hey, these are the things we can do. If it's not on this list, we can't do it. So if your board requires that, like, sorry, like upvote the feature and we'll get to you soon. So that's the part that we're kind of fleshing out now in terms of the user experience is a much clearer dialogue with the user about what constraints are on your board, what physics is on your board, what we can do, what we can't do, and then grading our homework and saying, hey, we have met these constraints or we haven't. But that's going to be a journey that continues for years, I'm sure, as we get into, faster and faster boards, more and more difficult boards, so on and so forth.
Totally. And I guess at this moment, how do you divide up your team between people kind of like researching the reinforcement learning to people kind of doing the engineering to other?
Yeah, so we're between full-time and part-time, about 20 people at this point, a little bit less. The vast majority of that is engineering, obviously. So what we think of as our compiler team is currently 11 or so people, and a few offers that have gone out with people starting soon, which is super exciting. We've got, I think, about 4 people right now on what we think of as the application team. So that's, UI, backend, infrastructure, all of that kind of stuff. And then we've got some folks on the product team in terms of like design, some electrical engineers who are using the product, informing it, building boards with it, so on and so forth.
Now, how do you run a team? This is a question I get a lot. Like, how do you run a team that's doing really new research? Like, are you able to actually operate to a schedule? Do you do sprints and sprint planning?
Yeah, that's a tough question. I don't know that I have great answers for this, to be honest. And if people do, I'd love to hear them. I think that we still try very hard to keep schedules and to keep focus, despite a lot of it being research, right? So we had, especially earlier in the company, we were in just pure research mode. And so that was a lot more exploration, finding papers, replicating papers, coming up with their own experiments, casting a wide net with a lot of different bets to see what works out. now we're kind of transitioning into a more focused, more fast kind of mode of development where we're a lot more clear about the goals, a lot more clear about the projects, have a higher bar to kicking something new off. And I think with research in particular, like there's still a lot of it that is actually just good engineering, right? Like if you want to run a good experiment, right, you have to set up, your environment, you have to ask a good question, you have to set up all of your instrumentation to track the question that you're asking, you have to collect the data, you have to actually make it run fast, all of that kind of stuff. And a lot of that is actually predictable good engineering work. But it's serving some, specific question that you don't know if it's going to go well or not. And yeah, I mean, I guess we just have to accept that like some of these things don't work out, and we try to focus on finding places where we think there's a clear path to make things better, a clear path to improve the models, the environments that will go straight into production, but also allowing some amount of time for bigger bets that might not work out.
Well, what fraction of the things you try really don't work out or really clear failures?
At the beginning, we had a lot. So one of the things that we tried to do was to borrow heavily from the chip industry. So there's a similar problem to this within chip design, which is actually laying out the insides of a chip. And on the surface of it, that problem looks really, really similar to this problem of PCB layout. And it's a lot more successful in automation, right? Like chips like an NVIDIA GPU that has 80 billion transistors certainly cannot be done by hand. It certainly must be at least partially automated. And so we've looked for a lot of research to try to duplicate, right? Different placing techniques, different routing techniques, so on and so forth. And unfortunately, the vast majority of them just did not work out for us for a bunch of different reasons. So we probably re-implemented, 15, 20 different papers that, we got similar results to what the paper showed, applied to the PCB problem, and it just didn't quite work. So it was quite a lot. By now that we've kind of formed our own internal approaches and thinking for how to do placement, how to do routing, how to couple it with agents. And I think our success rate on ideas is a bit higher than 99% failure.
Nice. I guess like one of the interesting things about your background is that you're not originally, you didn't study reinforcement learning or even I think computer science at all, right? Like, how did you get into the field and how did you get up to speed?
Yeah, so I got really interested in it like in 2015 or 2016 or so. And at that point, I saw Andrew Ng's courses. I was like, all right, this is going to be great. So I went through, the whole, all right, here's what a neural network is. Here's how the math works. Here's backpropagation, all of that kind of stuff. Wrote it all out from scratch to make sure I understood it. And then I just looked for places to apply it. That's really kind of it.
Like on kind of interesting problems, different types of things? Is that?
Yeah, exactly. So I think, I played around with a lot of the, what was it called? Kaggle challenges. That was super fun. Learned from some of the people who were succeeding at those, and then eventually when we got into starting this company, obviously, became a full-time job and had to step it up a notch.
And when you say you wrote it all out, the backpropagation, do you mean you kind of wrote it out in math or you wrote it out in code?
Both. So engineering's courses, I don't know if probably a lot of viewers here have gone through those. They're excellent. And he does both, right? He works through all of the math, the linear algebra, and how it gets represented, and then walks you through actual submissions of code. I forget if it was in MATLAB or something, or maybe it was Python. I don't remember. Or maybe it was Octave. I don't remember. But yeah, you actually write everything out as well, which is great.
Nice. I think it used to be MATLAB. Probably moved to Python by now, I'd imagine. Yeah. Awesome. Well, I guess two final questions. What's like another topic in machine learning or something else that you think is underrated or something that you'd look into if you didn't have this job?
So I think we alluded to this earlier, but I'm really excited by AI applications for physics directly, for physics simulations. It's one of the things that is like a lot of the papers published for PCB design and for chip design with AI are actually driven around exactly that, of like simulating, electromagnetics concerns or thermal concerns. And then once you have a model, you can do it, 1,000, 10,000 times faster. And then generation of candidates that can fulfill that increases. And so I'd love to see a large language model-esque approach to all of physics, right? Because that's a reusable thing, like language. It's a reusable thing that's going to apply almost everywhere. And so I'd love for there to be like an open AI of physics.
Totally. And you do see lots of different people working on different aspects of that, but I guess not all of the laws of physics at the same time, typically.
Yeah.
I agree. Super cool. And then, final question, which you kind of got into a little bit, but you'd be really someone to opine on this. I think, what has been the biggest challenge of kind of taking this kernel of a machine learning algorithm and making it work in the real world? I mean, you mentioned, sort of explaining to customers when things are failing and sort of putting a product around it that prevents people from shooting themselves in the foot. Has that been the biggest thing, or is there like something else that you spent your time on?
Yeah, no, I mean, that's definitely a big one, right? I think that one of the convenient things about our problem and reinforcement learning in general is that like we can actually have a pretty clear division between like the thing that creates candidates, right? And that thing is allowed to be faulty. It's allowed to not have perfect precision. But then you have a whole bunch of kind of classic code that checks every single rule that it can be met. And so we definitely focus a lot on that to make sure that like hallucinations, for example, aren't a problem and never would be. I think all of our other challenges around this are probably similar to everybody else doing research in AI in general, right? Like, generalizing across boards is proving very, very difficult. For example, right? Boards are everything from a tiny little thing with 2 components to these, 10,000 component monsters. And so how do you get an observation and a stack that like can actually vary across that and have a wide range of different actions available to it across that? That's something we're spending a lot of time on and definitely haven't fully cracked yet.
Interesting. That's super cool. Do you have any favorite applications of circuit boards built on your platform?
Favorite applications? So this is one of the boards that we designed that I was particularly excited about. So this is a computer vision board that's got a STM32 processor on it, a camera, USB connection, and then it runs right to a screen. And so this is a particularly fun thing to work on because we actually got to build something that can run onboard algorithms on it. And it's quite an old board, probably 2 or 3 years old, but it's actually fun to see, to like bring it up, play with it, and then actually be able to do some fun things like put a mustache on yourself, because as an ode to the Silicon Valley show.
Love it. Super cool. And I hear you're hiring in different roles. Is that right?
Yeah, definitely. Always hiring. Our careers page, at Quilter.ai. Please come visit if you're interested. We're looking for folks who are obviously experts in machine learning, reinforcement learning. Always welcome. But also in like C++, running CUDA kernels for some of these geometry algorithms and physics simulations, and so on and so forth.
Do you think there's anything particular that you look for in candidates that might be specific to you and different from other machine learning companies?
Yeah, I mean, we have a pretty strong focus on reinforcement learning in particular. So that's kind of an interesting thing where we actually look for a lot of candidates who are coming from like robotics, where a lot of this work is being done. And especially where, sampling the environment is expensive. Because that kind of is the case for us, is that the environment is not, super fast and trivial to sample. And so robotics deals with some of the similar issues, and that's why we look in that field in particular. We've had some folks also join from like self-driving car companies, because a lot of kind of path planning, routing, and so on and so forth smells a little bit similar to this problem.
That makes sense. Well, nice. Thank you very much. This is a really interesting interview.
All right. Thank you, Lukas. Appreciate it.
Thanks so much for listening to this episode of Gradient Dissent. Please stay tuned for future episodes.